Thank you very much. I'm Ahmed Badruzzaman, and I'm here under the sponsorship of the SPE Foundation, who are very generous in allowing me the opportunity to come here. I'm also very grateful to several colleagues in the industry from whom I have learned a great deal, and to Chevron, my employer, who gave me the time to come here. Now, the topic I'm going to talk about, determining accurately the remaining hydrocarbon, is a very important one, and I'll try to convince you of that in the next few minutes. So my presentation will follow this outline. I'll give some introductory remarks, mainly focus on the techniques that I'm talking about and the applications, and then give you a summary. Now, why is it important to look at the remaining hydrocarbon? And for that, we look at the energy demand and the reserves that we have in the world. The world energy demand went up by 18.6% between 1995 and 2005. It is projected to increase by 27% between 2005 and 2015. Oil and gas has been about 60% of the marketed energy consumption in the world for a long time. It's going to go up a little bit by 2025. So oil and gas is going to be around for a while. The proved oil reserves increased by 34% between 1985 and 1995. But in the following 10 years, it went up by only 17%. So we are in a little bit of a jam. And we have had some discoveries recently, but not multiple giant discoveries that can tide us over. And no matter what anybody says, renewable sources and nuclear together are not going to be able to make up the shortfall. So what do we go for locating the reserves? Well, we go back to where we had been before. We have left about 2/3 of the oil behind, hydrocarbons behind. We need to go after that. And for that, we need technology. So what are some of the technologies that have been tested to determine the remaining hydrocarbon, the stuff that we have left behind? Nuclear techniques, they're shallow, but they are direct. And they can see through steel casing, which is an important consideration for us. Electrical measurements, they're deep, but they're not direct. And they have a hard time going through steel casing, and they have salinity effects. But we have had some success using them in Indonesia. We have also looked at interval electromagnetic and seismic techniques. The electromagnetic techniques did better than seismic, but we still need to do a lot of work. And these are very expensive methods. You can take core, look at it in the lab, and they'll be the most accurate way of determining the remaining hydrocarbon. But first of all, they're not continuous, and they are very expensive. You can't really do them continuously. So we use them as a benchmark. So nuclear really is the primary technique that we use. So I'm going to spend a lot of time talking about nuclear. So what are the nuclear monitoring techniques? And there's a whole bunch of them. There is not one unique nuclear technique. There's several of them. So let me go through them. I'm a physicist, by the way. So I'm going to give you a little bit of physics here. Of course, I'm not going to give you a quiz after this. I'm just going to give you some physics. Now, the devices that we use a thing called a neutron generator. What it does, it sends out very high energy neutrons. The source is on for about 15 to 40 microseconds, depending on which vendor you're using. And during that time, these high-energy neutrons go out and hit different atoms. When they hit these atoms, they produce very characteristic photons as secondary radiation. So looking at the energy of those photons, you can tell what sort of atoms you hit. So this allows you to identify what you are interacting with. Now that's physics. How do I turn it into petrophysics? Or formation evaluation or monitoring? There are two basic approaches in the industry that we use. One is you take those photons that you located and you count them up, and if you identify the energy of them, you can tell what they hit. And if you take the carbon photons and the oxygen photons and you take ratio of them, you can construct what I call the oil saturation, the fraction of the formation filled with oil. It is a direct measurement because that C relates to hydrocarbon. The older method is, instead of looking at the counts as a function of energy levels, you look at the counts as a function of time. You sum up over all energy levels and you look at the function of time after you've turned the source off. Well, of course, their population is going to go down because the source is gone. Now, if you have salt water, the population decreases very fast, and you can get an idea of the water saturation. SW is water saturation. You can also get an idea of the residual oil saturation. If you have freshwater oil, which is what you would have in a water flood, you would not be able to tell the difference by this method. So you have to go back to the carbon-oxygen method, the top figure. This takes about 1 to 2 milliseconds, usually 1 millisecond. The first measurement is a few microseconds. The second measurement is a few milliseconds. Now, if you wait long enough, then you can see a third reaction that is going on. And okay. Oh, by the way, if you have gas or steam in the system, the decay is different, and this is one way by which we can identify gas or steam. In fact, we can quantify how much steam we have pumped in a heavy oil reservoir to pump the oil out by this technique. Now, if you wait long enough, you can see another burst of radiation, and that comes from by making the water that you have radioactive. If water is coming into the perforations, the water becomes radioactive, and after 7 seconds, you release the radioactivity, and you get a signature of where the water is coming in. So there is a whole bunch of measurements here that we can do just from one single physics. Very, very powerful, fascinating technique. The question is, how well do this do? Well, so in our world, of course, we're looking at counts, but we record the results on a paper or digitally versus depth. We call a log. So this is what a log looks like of a carbon-oxygen log. Very, very noisy. Now, what is the color scheme? The color scheme is I run this device 3 times here, just so that I get enough counts so that my statistical error is believable. You can also log very slow, but if you try to log slow, your cables start jerking, so you really can log only so slow. Some of the other learnings with this technique is that the porosity should be more than 12%. And you must know the lithology. Why? Because remember, it's a carbon signal. Now, if your lithology is calcium carbonate, you're going to get a carbon signal from that too. And you want to be able to tell the difference between the carbon from the oil and the carbon from the rock. So you need to know what type of rock you're dealing with. Remember, I said this is nuclear measurement, and nuclear measurements are shallow. So you really need to know what's going on in the immediate wellbore environment. Also, because you are doing monitoring, you should have some reference data which came from your open hole logs. So all of those things are important to be able to get a decent interpretation. What do the devices look like? Now, these are 2 modern tool designs that you have here. One is the centralized, where the detectors are sitting along the axis of the device. Now, in all nuclear tools, you need to have the tool pushed up against the borehole wall because they're shallow, so you need to have them as close as possible to the formation that you are trying to measure. Now, the centralized design, all vendors have this. The focus detector design is by one vendor only. Now, the centralized design is best for using in observation wells where you know you have water in the borehole. That's not going to impact your answer. You can tell the oil in the formation. Because if you have any significant amount of oil in that centralized detector design, that's going to overwhelm the signal, and you're not going to see much of the formation. The focus design, on the other hand, the near detector is seeing the borehole more, and the far detector is seeing the reservoir more, so you can distinguish the oil in the reservoir and oil in the borehole. That's an interesting trick. Now, one other thing, all these tools are slim. In the old days, they used to be fairly thick. The modern tools are very slim, so they can go through very complex geometries. Also, you can get multiple measurements with the same tool. In the old days, I have 4 measurements here. You needed 4 tools. Now, you can do it with one single tool. Okay, so what are some of the successes we have had? Well, this comes from Indonesia. 3-4 years ago, we noticed that we were pumping a lot of water out of these reservoirs. 99% of the fluid that we produced was water. So we went back to this well and we ran this carbon-oxygen log. And the carbon-oxygen log here, it shows that I have a bump here and I have a bump here. That means I have high carbon density. That means probably a high amount of oil. So what we did is we took this and we perforated here and perforated here. And after we did this, we pumped oil, and the water cut was down to 52% from 99%. So we have significantly increased the oil output from this well, in fact, from this field. So this was a big success for the carbon-oxygen technique for us in Indonesia. I'm going to go back a few years earlier because that's a success that I always quote. And that's not just carbon-oxygen technique, but the other decay technique that I mentioned. Now, in Nigeria, we had an issue. We produce a lot of associated gas with the oil, and we flare. It's not a great idea to flare this stuff. So we need to locate where the gas is accumulating, and then we need to locate where the actual oil is sitting now after you produce for many years. So we used a combined technique. Remember the decay curve that I showed you, that in gas it has a certain rate of decay? We used exactly that technique here and identified this to be the place where the gas cap has built up. Now, of course, in those days, we really didn't trust this technique. So we went and ran the open hole technique here, and it also confirmed what we saw. Okay, so we knew that this is where the gas cap was. We ran the carbon-oxygen log, and this is where the oil was. Then we perforated here. When we perforated, this is what we got. Before we did the log, the assessment and perforation, we are producing a tremendous amount of gas. After this workover, our gas production went down significantly. So that now we are just producing more oil, a lot more oil than gas. And this was a big success, but as I'll show you, this has not always been the case. So what are some of the technical challenges that we faced? I mean, if everything went so fine, we'd be happy, but we really were not. One was, we found that there was differences in the results that the vendors gave, even when we ran their tools in the same hole back to back. Then we found that these devices were not very well calibrated compared to the complexity we as the operators ran these devices in. And there were some long-term issues. People change tools. In a monitoring world, it is dangerous to change tools because you have to come up with a reference. And anytime you change a geologist who knows the field, there's an additional learning that you have to put in. And there are some fundamental limitations of the technology. So the question is, can you be confident about this technology? So how did we go about building confidence? And this has been our approach. Trust but verify. Can somebody tell me who it was that uttered those famous words in dealing with the world? Yes, Ronald Reagan. Trust but verify. So we apply that philosophy, but how do you do that? Well, you do field tests of these devices. We trust what our service companies are telling us, but we still need to verify ourselves. We have in-house processing techniques that we use. We have in-house R&D capability that validates what these guys are doing. Sometimes that has led us to develop our own algorithms. We have expert on-site users. And we have now recommended that wherever possible, we need to design monitoring programs up front before you develop the field. It should not be an afterthought. A lot of times monitoring is an afterthought. Comparison of 3 vendors. And this is what I was talking about, the variation among the vendors. This goes back a few years. We ran 3 modern carbon oxygen tools in a field in Texas. This is the 0 oil saturation. This is 100% oil saturation. And you see that the 3 tools, and we ran them back to back. And you notice that in some places, all 3 agree. So we're very happy about that. Some places, 2 of them agree, and the third one is sitting somewhere else. In some other places, the other 2 agree, and the third one is sitting somewhere else. It's really not good for my confidence in these devices. So what we did is we took that raw data and we processed it ourselves using our own processing algorithm. And that gave us this curve where we see the difference is significantly lower. The question is why? Why? First, two things we noticed. One is when you looked at the raw data, they look very similar. What's happening is that they take the raw data and they put a black box. Each of them have their own little black box, and they come up with a different answer. At least with our black box, we get a consistent answer. So, because there is no normalization between the different vendors' black boxes, and that's something that we really need to look at. But that didn't solve all our problems, because we deal with life a lot more complicated. So complex wellbores is the first one that I'm going to touch on, and second one is going to be complex formations. Now this is a sampling of the complicated wellbores that we have studied using these techniques. This comes out of Nigeria, this comes out of Angola, and this comes out of Indonesia. Large borehole, this is the device. The yellow thing is the device. Extremely small device. And any little bit of oil sitting in that blue stuff is going to kill it, because that's what it's going to see rather than the formation. Then we have this thing called blast joint. That means you put in the thick tubing so that when sand comes in, you don't really erode the tubing as badly as you do if you have normal tubing. This is one complexity that we have. These are the perforations. We have dual tubing strings and so on. I mean, we have a whole variety of these things. This is just a sample. Here, this is gravel pack completion out of Angola. Here, the device here, sitting here, has to see through a base pipe, a screen, a gravel, casing, cement, and this is a shallow measurement. Okay, so this is going to be tough. And this, in Indonesia, what happened is they had a horizontal well. For some reason, the casing set at the bottom, so this was not calibrated. The bottom line here is these conditions are not calibrated. It is going to be hard to calibrate, so how do we handle that? Well, we have a simulation technique that we borrowed from US national laboratories that we can, in 3 dimensions, simulate the response of these devices in these complex conditions. And what do I mean by that? What I mean by that is exactly what you do in the experiment, except on a computer, mathematically, you send out these signals, they go through and get lodged in the detector. So looking at that, this is one side view, this is the top view. I can see that the signal here in this device comes from about 6 inches. So that tells you about how far this device sees. And so I'm going to apply this trick on this. Why am I doing this? Well, in Nigeria, we ran this log with a slim tool, very large borehole, and the carbon to oxygen ratio was very high. Now, remember I said carbon to oxygen ratio is an indicator of the oil saturation, how much oil you have in the reservoir. The vendor told us that after 25 years of production, we still have 101% oil saturation. Didn't really make sense. And our geologists didn't really believe it. Didn't believe that explanation. Their explanation was because you have a thick tubing here, that's what is changing those wiggles that I showed you early on. Well, we studied this with this modeling, and this is what we saw. That the signal really is not coming from the formation. I don't really see anything coming from the formation, but I see a lot of signal coming from the borehole. So this is a complicated borehole where the oil was stuck, I think, and it is the oil in the borehole that you are seeing, not 110% oil saturation. So our recommendation was flush the borehole. Now that has its own challenges. Or identify what you have there and quantify how much oil you have in the borehole so that you can correct for it. If you cannot do either, do not use this technique. Okay? That doesn't, of course, make my vendor friends happy, but that's what I'm paid to do. Using this very carefully calibrated approach, we were able to increase the production by 30,000 barrels a day in this field. But challenges still remain. Another complex condition, another vendor, another part of the world, and we are looking at a different deal here. Now this is gravel pack completion. Remember I showed you it has to see through those multiple layers of things? Well, here, this vendor, what they do is they've come up with a line where there's 0 oil saturation, 100% oil saturation. They run this device, and if the signal from the device sits in the middle, you say, oh, yeah, I got 50% oil saturation. Pretty straightforward interpretation. So this is what we did here. 100% oil saturation, 0 oil saturation, and this is in the middle. So you'd think this is 50% oil saturation. Unfortunately, remember early on I said we have noisy data, so you have to run this multiple times, and I'm glad we ran it multiple times. Because when we ran it the second time, this curve shifted from here to here. Third time it shifted here. So this curve was dancing all over the place. So which one do I trust? In fact, I can't trust any of them. This is really useless data. What is happening is that because of these perforations here, there is a communication between different zones, so oil was coming in and out of the wellbore. So this is really useless data, and no amount of fancy modeling on my part is going to help it. Okay, complex formations. Steam flood, I'll talk about it at length. Water flood, we have had great success where you pump in water to push out the oil in several parts of the world. Water and steam flood mix, we are having some challenges in that. Water flood in diatomite, I think we have come to some understanding of the problem. Diatomite, by the way, is a very high porosity reservoir. The porosity there is 70% compared to standard high porosity is 30%, 35%. CO2 flood is another problem that we looked at. And we have had some challenges with shallow gas hazards in Thailand, for example. We don't want to drill into shallow gas hazards. We need to locate where the shallow gas is, so we're looking at that right now. Let me just concentrate on the steam flood. Now, in steam flood, you start with the oil-water mixture, you pump in steam, and you now have a three-phase reservoir. So you need to correct for the steam. Now, the carbon-oxygen method directly does not do that. So we derived from theory an equation that takes the oil saturation from the carbon-oxygen log and corrects it for the steam saturation. Now, how do I get the steam saturation? I get it either from the decay curve or a neutron log. So using this fancy technique, I can get the oil saturation when you have all three phases together. How well does it do? Kern River, California. It does extremely well. These dots are the log data, and this is the dots are the core data, and the lines are the log data, and the black line is the open hole Archie data, and the blue line is the carbon oxygen data. Extremely well. In fact, field-wide, we were able to reduce the uncertainty in this to less than 5 saturation units. Grand success. We identified over 300 million barrels of remaining oil in this field. So we use this to estimate our reserves and make well decisions where to drill the next wells in Kern River, California. So we thought, boy, we have solved the problem. So we introduced the technique in other California fields and in Indonesia, in the big giant oil flood in Indonesia. Of course, nothing works like charm, so we get in trouble. What sort of trouble? And let me show you the example, the other California field. So we were here, great match. Now we are sitting here. The core and the log really do not match at all. The dots are the core. It's all over the place. And the operator really didn't trust what we were doing. So we undertook an internal study. The internal study revealed some things. It revealed that the lithology, the rock formation, was a lot more complicated than in Kern River. So the core samples we took were not really representative of what we were doing. The calibration was not sufficient, and the log data was poor. So we have now developed our in-house algorithms by which it looks a lot more promising, and we have just run 100 wells, which looks very good, and we'll be presenting results on that. The bottom line here is that we had to do ourselves a lot of analysis and development to be able to get meaning out of these results. So the impact of using the technology in an informed manner was that we were able to get great benefit out of this in several parts of the world, from Nigeria to Indonesia to Kern River, California, and so on. The important thing is you have to be an informed user. You just can't use things blindly. So I'm going to skip the next slide and mention a few best practices. Job planning, job planning, job planning. If I say one thing over and over again, this is the one I'm going to say. You need to pick the right technique. You need to pick the right tool. You need to decide how fast you're going to log. So you need to decide that upfront. You can't just do it on the fly. Do you have good open hole or core data that's used as a reference so that I know what I'm monitoring, because I'm monitoring change? Choice of wells. obviously that gravel pack well that I showed you is not the place where you should be running these tools. So you need to know what you are doing. You need to know the lithology and the dynamics of the borehole. In our case, having the ability to validate these results independently of the vendor and having the in-house R&D capability was big help. Having a case tool specialist on site and training him or her well was also a big benefit. But my question is, if you do all of this right, are you going to get a perfect answer every time? No. Why? Because there are two fundamental limitations of nuclear techniques that you need to be aware of. One, they're statistical. In other words, you're looking at counts, and if your counts are low, you're going to get very poor statistics. Big uncertainty in your answer. In fact, the current logging tools all in the industry, used in the industry do not have sufficient counts, oftentimes. The resolution of the detection system, you're trying to identify elements. That means you're trying to identify discrete elements. The better resolution you have in your detector, the better you're going to see that. The current detectors are not quite there yet. But we can adapt technology from the U.S. national laboratories or universities. They are developing some of these techniques. And I'm ashamed of stealing technology, but I'm not ashamed of borrowing or begging technology out of these institutions. So some of the challenges, then I'm going to finish in a second. One of the things we found was that monitoring was mostly an afterthought. We had these old wells, we just stuck in a tool. That's not what it should be. You must be cognizant of the limitations of the current instruments I just mentioned. You must have good calibration. You must train your user, because if you have a desperate user who wants an answer, and if a very eager vendor, you're going to abuse the technology. He's going to sell you something that you don't want to buy. Okay? And the last few years, this is a pitch I make for hiring young people. Last few years, we have reduced the R&D in this business, in the oil business, and we need to jack it up so that you get young minds, a lot younger than I am, to take on the charge. So the summary is, locating remaining hydrocarbon is critical for the world's future. We have left behind 2/3 of the oil that we have there. Frankly, I don't want another war. Advanced techniques have really helped to identify reserves and make better decisions where to drill those wells. But these techniques need very tender, loving care. Remember my title? Art or science? What do you think? Is it art or science? Any answers? It is both. It is art and science. And sometimes I think it is magic. And more challenges lie ahead. So what I would say is, we as an industry push for advancing the technology, advancing the practice of this technology, and form partnerships to do that. But I don't think any of us can do it alone. Thank you.